I also believe you can see my screen.
Yes, sir.
Good. Today we're looking at experiment 26 in your manual, and that is titled Verification of Planck's Constants by Photoelectric Effects. Verification of Planck's constants by photoelectric effects. We shall be achieving this by making use of photoelectric effect simulation, made available by the University of Colorado, USA. And you can actually download that photoelectric effect from phet.colorado.edu. So once you get to that page, you can search for photoelectric effect, then you will be able to download it. Note, it's a Java file, so you must have Java installed and updated properly in your system for you to be able to use the Java application. Now, the interface of the Java application looks exactly like what you have on the screen. We shall be using it in real time shortly. Let's quickly have an overview of what photoelectric effect is all about. It's one of the key experiments that supports early quantum theory. Now, quantum theory is basically different from the usual classical theory. The reason being that oftentimes things you cannot observe classically are observed and measured and quantified using a quantum theory. Okay? Prior to 20th century, light was considered as a phenomenon to be a wave or a wave phenomenon. And in most ways, this idea actually reflects reality very well. For instance, light is bendable when it passes through a lens. Now, Planck put us on the path leading out of this ticket of confusion when it theorized that light and other forms of energy comes in packets or discrete bundles. Now, in this theory, light is now considered to be a particle. Remember earlier, it was considered before the 20th century as a wave phenomenon. Wave phenomenon in the sense that it exhibits the properties of waves. However, with Planck's insight into this theory of light, it's discovered that light also behave as a particle, okay? And this particle of light, or this district or packets of light, is called a photon. So unlike having a continuous spectrum of energy flowing, light is actually in packets. The reason why you cannot see it as a packet is because the time interval between the packet is so infinitesimal that you might not be able to pick that out. Light in the black body radiation experiment coexist only in discrete bundles with energy given as E is equal to hv, where V is frequency. P is frequency. You may see this formula written elsewhere in some textbook as HF, where F will stand for frequency. But in this case, we're using V. So he is equal to HV, where your H is the Planck constant and the E is the energy. Okay? This equation can also be expressed further as Hc over lambda. This time around, where your C is the speed of light. C is the speed of light, and lambda is the wavelength. Okay? So you can infer from this expression that your frequency V is equal to C over lambda, where C is the speed of light and lambda is the wavelength. Okay? Now, different metals hold on to their electrons more strongly and weakly due to atomic structures. And so the work function for various metals varies, as we will see in the table shortly. The kinetic energy of the electron refers to its actual movement once ejected. Now, due to atomic structure of every metal, you expect that all the electrons are stable and they are held together in their position within the material, within the metal, okay? However, it's possible for this electron to be ejected out of their place. And when an electron is ejected out of a metal surface, of course, it will be ejected with a kinetic energy due to motion, okay? So, and this is represented as EK, kinetic energy, okay? The EK can effectively be ignored if we just reach the amount of energy to loosen the electron, but not getting it moving. Now, I said earlier that electrons are tightly held together by the bonding existing between them in the metal, okay? And these electrons can be ejected when a photon of energy falls on that surface, okay? Now, this electron, when they are ejected and is able to move out of its position, is actually moving out of the position with a kinetic energy. However, if the photon energy you release on that material is only sufficient to remove the electron out of its position, but not to give it a motion, is that okay? Then the kinetic energy can be ignored. Okay? And the formula that relates yes, HV is equal to EK plus phi, where your phi is a Greek alphabet, where your phi is the work function. So what is work function? Work function is the energy required to remove the outermost or the highest electron on a metal surface, okay? Is the energy required to remove the highest on a metal surface, okay? We will see the definition shortly. Now, H, as usual, is your Planck constant, and it has a value of 6.626 times 10 raised to power minus 34 joule seconds, okay? This same Planck constant can be expressed in electron volt seconds. And when this is done, you have the value as 4.14 times 10 raised to power minus 15 electron volt seconds, okay? So this constant is what is referred to as Planck's constant, okay? EK is a kinetic energy of the ejected electron, and phi is the work function. If photon has enough energy, electron emerges with kinetic energy, which will be equal to photon energy minus the work function. Let me quickly explain. I just said now that if you have the kinetic energy, okay? Or sorry, if you have an electron that is able to move out of the metal surface with the kinetic energy, the kinetic energy can be calculated as the total photon energy applied to that material surface minus the work function. What is work function? Work function is the energy needed to kick the highest electron out of the metal. Okay? Remember, the electrons are held together. They are bonded together on the material surface. Okay? For you to eject it, you need to overcome the potential energy holding them to that place. Is that okay? And so the minimum energy you require to release electron, just release it to be free to start with, okay, is called the work function, okay? So if you release, say for instance, you release 20 electron volts of energy, of a photon energy to a material surface, is that okay? And the work function of that material is 18 electron volts. Okay, then the kinetic energy that will be available for that electron to move around will be what? 20 minus 18, and that will give you 2 electrons.
Yes, sir.
Okay,
I can see
can
your
you also see
screen.
this?
Yes, sir.
Yes,
Okay,
sir.
good. Now, the material of interest is platinum. I said we have other metals here: sodium, zinc, copper, platinum, calcium. So platinum is the metal of interest. Okay, the light, set your light intensity to 100%. This is my light intensity. Okay, I set it to 100%. Okay, and vary wavelength from 100 nanometer to 160 nanometer. You can type the wavelength value directly instead of using slider. Okay, so I have 100, so I can type directly. This slider can change this wavelength. Is that okay? This slider can change it. Okay, however, I'm interested in just typing 100. Okay, so type 100 and press enter. Okay, and once you press and type, what we are interested in doing is you are measuring the current directly from the simulation. Okay, and I have my current here. Don't bother to change the voltage. So the current is 0.882 or 100 nanometer. I change it again to 110 and press enter. So the current is 0.971. I change it to 120, press enter, and I have current 1.059, and on until you get to the last value. Okay, once that is done, you are expected to compute or complete the table above and plot the graph of E in electron volt against frequency V. Okay, now how do you compute your frequency? Remember earlier we had said your V, frequency V, is equal to what? C over lambda. Is that okay? C is a constant. It has a value of 3 times 10 raised to power 8 meter per second. Okay? And this is wavelength given in nanometer. Nanometer simply means this value 100 means 100 times 10 raised to power minus 9 meter. Okay? So don't forget this nanometer. This 100 times 10 raised to power minus 9 meter. The same thing with 110 and on and on. Okay? So with that, you will simply have 100 times 10, excuse me, you will have C. V is equal to C over lambda. So your C is given as 3 times 10 raised to power 8. Then you have this. So once you divide it, you get a value for your frequency. And your photon energy, you use the formula E is equal to HV, or you use HC over lambda. Is that okay? But remember, you are calculating it in electron volts. So the H you will use, the Planck constant you will use, will be this value. Okay? You will use 4.14 times 10 raised to the power minus 15 electron volts seconds. Is that okay? So once you're done with that, then plot the graph of EV against, energy in electron volts against frequency. And from your graph, deduce Planck's constant. Okay? So you should be able to know how to do that. Then taking the average of the data in the table above, determine the initial kinetic energy of electron as it comes out of the metal when the platinum work function is given as 6.35 electron volts. Okay? Now, this procedure and this experiment you have here, you are to do it on your own and keep it to yourself to start with. Okay? By tomorrow or next, an exercise or a quiz will be made available to you online based on this. Okay? You are expected to do this one before the period is over today and master the usage of the simulation and everything you have to know here. Okay? So by tomorrow or next or Friday, a quiz will come online for you to be done based on this. Okay? So please take note of that. It's quite very important. Now, having said that, you can have access to this material on your LMS. Okay? So the material is available for you on your LMS. I have these materials uploaded for you already on your LMS. So if you go to your course home page, so you have this available to you, Photoelectric Simulation Week 8. Okay? You can download the jar file that you need here. That's Photoelectric Effect. Or you can go to the website of phet.colorado.edu to download it from there. And the PDF I just used now is here for your guide. And then I'm opening this right away for your attendance. You'll be able to fill the attendance in the next 15 to 20 minutes. Thereafter, it will go offline. Okay? So you can also access the link for the attendance here very quickly.